So it is a great pleasure to welcome Rebecca Bauer. So she did her PhD at the University of Edinburgh and then moved to the University of Oxford, and has recently started her Ernest Rutherford Fellowship and is working on galaxy evolution at high redshifts, which is what she's going to be speaking on today. Over to you, Rebecca.
Thank you very much, Sarah. It's really a pleasure to be here. Let me just share my screen. It's not the right slide. Okay. Can you see that fine?
Yes, thank you.
Can you see my pointer?
Yes, it's moving around.
Okay, great. Okay, all right. Yes, so the topic of this talk is galaxy evolution at high redshift. And when I was thinking about what I was going to kind of overview today, I came across the kind of basic question of, what does high redshift really mean? And unsurprisingly, like a lot of things in astronomy, it depends on who you talk to as to what they say is high redshift. So a few examples here. A cosmologist might say high redshift is 1000, 1100, corresponding to when the cosmic microwave background light was emitted. But I spoke to some of my group members yesterday who work on H1 astronomy, and they say that redshifts greater than 0.1 is what they define as high redshift. And that's purely because that's the limit of their observations at the moment. So you can see already a huge difference in what people define as high redshift. A logical person might say redshift greater than 1, which would be less than half the age of the universe. And a galaxy evolution person might say redshift greater than 2, which would be based on beyond the peak in the star formation rate density, which I'll talk about in a bit later. So just to kind of clarify what I'm talking about in this particular talk is the range redshifts 5 to 12. And the reason for this is that corresponds to around the first billion years of the lifetime of the universe. It also overlaps with the epoch of reionization, which is a really fundamental time in the evolution of the universe. And the redshift 12 upper limit there is really a bit arbitrary. It could certainly go higher. But the reason I put 12 there is that's the current observational limit for the most distant galaxies that we know about are redshift 12. So the table on the bottom there just shows you the redshift along the top and the age of the universe. So you can see, redshift 5 is when we start to get close to the first billion years. And by redshift 12, which is our current limit, we're already 370 million years after the Big Bang. So really getting very close to the early universe there. So some of the sources that I'm going to be showing you today are kind of highlighted in this nice press release on the right here from quite a few years ago now. And the background is a very deep image, the Hubble Ultra Deep Field, and the little diamonds here illustrate some of the most distant galaxies we've known to date. And so this kind of shows you along the top what these galaxies look like, and this is the kind of thing I'm going to be talking about today. These are very, very distant, very, very fascinating sources that tell us about the very early universe and galaxies at this time. So what was the universe like in the first few billion years then? Well, from theoretical arguments predominantly, but also some observational arguments, we think it has very low chemical enrichment, maybe even zero chemical enrichment for the very first stars and galaxies. And this is because the fuel for these early galaxies is very pristine. It's only what was left after the Big Bang. So this is hydrogen, helium, and a trace amount of lithium. So this changes the whole chemistry of these early galaxies from what we might think of as like a galaxy locally. We know that there are supermassive black holes. We have observations of these, and we know they exist in the first billion years and that they're accreting. But there are many, many questions about black holes in the early universe. And really what we have observed and what we know about is the tip of the iceberg in terms of black hole formation in the universe. And we also know that the universe was predominantly neutral in the first billion years. And by that, I'm talking about kind of, if you add up all the atoms in the universe, these are the atoms that are in the intergalactic medium and surrounding galaxies. These are predominantly neutral, and it's through the action of galaxies pumping out photons, ionizing photons, and blowing bubbles around them of ionization that the universe changed from being predominantly neutral to being predominantly ionized as we see today. And this process is called the epoch of reionization. So I already mentioned a little bit about the observational frontier, and this is a really nice diagram which shows some of the very early galaxies found by the Hubble Space Telescope on the kind of timeline of the universe. So on the right is the Big Bang. This was followed by what we call the cosmic dark ages, where there were no stars or galaxies. And then this was ended by the formation of the first stars and galaxies, which we think happened around redshift 20, but really we don't have the data to say too much about this at the moment. The observational limits for very distant galaxies are redshifts 11, some redshift 8.7 object as well. So these are galaxies, as I said before, in the first 400 million years after the Big Bang. So how is it that we can observe these sources, and what exactly are we observing to find these very high redshift sources? So to illustrate this, I'm showing you here a nice kind of cartoon of what the spectrum or the spectral energy distribution of a star-forming galaxy looks like across a wide range of wavelengths. So I don't believe that anyone really has this full data for a single galaxy, but by piecing everything together, we can get an amazing idea of what this should look like across this huge wavelength range. So on the left, with this blue line here, we're seeing the stellar light from stars. So in a young star-forming galaxy, this is mostly coming from O and B type stars, and their spectrum peaks in the ultraviolet part of the spectrum. So as well as the stellar continuum light, the photons from these stars also ionize the surrounding gas, and this then emits nebular emission lines as these atoms recombine. And that's what's shown as this kind of grey, sort of spiky spectrum here. And so added on top of the stellar continuum, you see these strong emission lines from the ionized gas. If there was an AGN in this source, then for comparison, the AGN emission, so this is from the accretion disk, the hot accretion disk would look something like this blue bump here. And if there was a dusty torus in the AGN, it would peak around here. But I'm not going to talk about AGN today, so focus on the starlight. So then as we go to very long wavelengths, what we start to see is the emission from the dust. And so if there is dust present, which is still a bit of a question mark at high redshift, it absorbs the UV photons, and these are re-radiated as into the far infrared, effectively as a thermal emission. So this is like a black body type curve here. And to give you some idea, the dust in the high redshift galaxies is typically about 50 Kelvin, which we say is hot dust. So to think about how we'd actually observe such an object, a star-forming galaxy at high redshifts, basically you can forget about everything that I've grayed out here and just focus on this small part of the spectrum here, which is the rest frame UV. And this is because, obviously, as we go to high redshift, this UV light is redshifted, well, the whole spectrum is redshifted significantly for these very high redshift galaxies. And it means that when we look in the optical and near infrared, where most of our very deep imaging data is, what we're seeing is the redshifted ultraviolet part of the spectrum, which is just this tiny part here. So typically we find these sources by looking for objects that look like this in the rest frame optical and near infrared, sorry, the observed optical and near infrared, apologies. And the two main selections are based on this emission line, the Lyman alpha emission line here, or we select them based on this continuum emission here. And we call these Lyman-break galaxies, which I'll explain more in a second. So just a caveat here, and something you can maybe think about during the rest of the talk, is that I grayed out this huge part of the spectrum because we just don't really have access to that at high redshift. So all the inferences that I'm going to make in this talk that others have made as well, like the star formation rates, the morphologies, the luminosity functions of galaxies at high redshift, are only based on the rest frame UV light. So you can think about what might be the possible issues with this inferences, and we can talk about that in the questions if you like. So before I move on to just explain the Lyman-break selection in a little bit more detail, I wanted to mention some other high redshift sources that we know about. And these are more extreme and rare objects that, in comparison to the kind of standard selections I just mentioned. So there are gamma ray bursts that have been associated with very high redshift, to be at very high redshift. For example, this is an object at redshift 7.8 from Vera et al. And what you're seeing there is the afterglow of the gamma ray burst, and you can use that to estimate the redshift. And these are really interesting objects because they typically pinpoint very low metallicity galaxies that would be too faint to be found otherwise without this incredibly bright afterglow. And then on the right, I'm just showing you an example of a source that's been selected, not based on the rest-frame ultraviolet light, but on the rest-frame far-infrared emission, the dust. So if a source is incredibly dusty and very highly star-forming, so thousands of solar masses a year I'm talking about, it becomes very, very bright in the far-infrared. And in fact, this is a redshift 6.3 galaxy that was found by Herschel in the far-infrared, and you can see here the black body type spectrum. But these are very extreme sources, so they're not really representative of typical galaxies at high redshift. So this is a little movie which demonstrates how we actually find these high redshift Lyman-break galaxies, and I'm going to show it a few times so you can get a feel for what's going on here. But essentially, the grey part here is the simulated spectrum of a high redshift galaxy, and the redshift is shown here, and this will increase through the video. And the coloured lines here are the different filter curves of the Hubble Space Telescope. And then finally, along the bottom here, shows you what you would see in each of these filters at a given redshift, right? So at redshift 3, you can see this object in all the different filters. So hopefully this is playing for you now, and it's going to just loop over, so I'll just talk over it. So what you can see is as the galaxy redshifts, we identify a very, very strong break in the spectrum, and this is this Lyman-break that I keep mentioning. Now this is really important because it makes these objects quite easy to identify. So if you look along the bottom, you can see that essentially the galaxy becomes invisible on the short wavelength side, but is still visible on the long wavelength side. And we use this very distinct spectral signature to find these sources and to estimate their redshift. So to understand why we see this very, very strong break appearing in the spectrum, this is another video which I think is a little bit clearer as to what's going on. So this strong spectral break is caused by intervening neutral hydrogen along the line of sight between us and the quasar or the galaxy. So as the light comes through the universe, it encounters neutral hydrogen, and it also gets redshifted, the light. And what this does is it causes absorption, which I'll show you now. So this is a really nice movie from Andrew Ponson which shows this in action. So you can see along the top the intervening neutral gas, and on the bottom is a spectrum of a quasar actually, but it's very similar to a high redshift galaxy. I'll play this one again as well. But what you can see is as it goes through, the spectrum light goes through the different gas clouds, it's absorbed at that wavelength, and that causes this kind of deficit in the spectrum. So I'll just play that one again for you. So this is a Lyman alpha line. This is where the Lyman-break is going to be. And you can see all this absorption starts to appear in the spectrum. And this is just due to the light passing through this gas on its journey to us. So the other key, the key factor here is that as we go higher and higher redshifts, we enter into this epoch of reionization. And within the epoch of reionization, there is a lot more neutral hydrogen than at lower redshift. And what this essentially does is, apologies for the very poor drawing on this slide, what this essentially does is it completely absorbs all of the flux in the spectrum. And so you get a very strong step or break in the spectrum here. And my scribbles here are just to show you that there's no flux once you go into the epoch of reionization. So fundamentally then, the technique of finding these high redshift galaxies is quite simple. And what we're doing is using these broadband photometric filters and images and looking for things that have a spectrum that's basically like a step here. So this is just an example of how we actually do this in practice, just taking the example of a Redshift 7 galaxy here, which has a break around 1 micron. For a Redshift 7 galaxy then, we would expect to have a detection in the Y and the J band here and not in the Z band. So this is a red optical filter and these are the near-infrared filters. So we can identify something with a step by using a color-color diagram. This is quite a traditional approach. And essentially what we're trying to do is find something which is very red between the Z and the Y band. So here between these two filters, but kind of flat between the Y and the J. So what people do is they draw a box on this diagram, and then within this box is predominantly high redshift galaxies. Another similar complementary approach is to use more of the filters, so not just 3. We have many optical and near-infrared bands, and we can fit to these bands with simulated galaxy spectra. So that's what's shown in this plot here. Again, it's a Redshift 7 galaxy. We see the Lyman-break in the data, which is the black points, around 1 micron. And we fit different galaxy templates to it and get the best fit model and the best fit redshift. And in this case, the best fit model is this blue line, which is a Redshift 7 galaxy. But there are also other models that can fit the data to different degrees of goodness of fit, I guess. For example, this red curve is the kind of next best fitting redshift curve, but you can see it's not doing a very good job. So this kind of on the surface simple method, is complicated by the fact that the high redshift galaxies we're interested in are typically some of the faintest objects within the imaging data we're looking at. And the other complicating factor is that there are other lower redshift, I would say less interesting objects that can mimic the colors of a high redshift galaxy. So this is the main issue that we face when trying to find such sources. So in the challenges here, we have contamination by low redshift galaxies. So that's what this red line is here. This is a Redshift 2 source, where this is what's called the Balmer-break that can mimic the high redshift Lyman-break we're looking for. There are also brown dwarfs in our own galaxy, which can have quite red colors. These are very cool dwarfs. Their spectrum peaks into the near-infrared. And that's what's shown in this color diagram here with the stars. So these objects, if you imagine a bit of noise on here, they could pop in and out of this box and be identified as a high redshift source, when in fact they're not. And then just due to the fact that we're often pushing the data very hard to find these very exciting but very, very faint sources, sometimes we do in fact encounter artifacts that can look quite similar to high redshift galaxies. So there's a lot of work spent in really cleaning the samples and being very confident that we have a true high redshift galaxy. Okay, so once we've assembled these samples of Lyman-break galaxies using the different filters that we have, the next thing to do is to measure the number density of sources. This is like one of the most fundamental measurements we can make of galaxies. And this is encapsulated in the luminosity function, an example of which is shown here, where this is the number density on the y-axis per unit magnitude, so per unit luminosity that is, and per unit volume in the universe. So what this shows is that, this is the absolute UV magnitude here. What this shows is that there are many more faint galaxies than there are bright galaxies. But also really interestingly, if we plot this number density as a function of redshift, what we see is an evolution in the number density of sources. And this is what we would expect just through thinking about structure formation. Galaxies are building up as the dark matter halos are building up in the cosmic web. So on this plot, you can see that Redshift 8, the highest redshift sample they had, and between Redshift 4, there's a factor of maybe 10 increase in galaxies with a certain luminosity. And so there are now tens of thousands of high redshift galaxies, so redshifts greater than 4 in this definition here, found within very deep Hubble surveys. such as the Hubble Ultra Deep Field. And the reason why Hubble's been so successful at doing this is because, as I showed in that first video, it has these near-infrared filters which allow you to find these galaxies at higher and higher redshifts than you could before. So, as well as being a kind of essential first measurement you make of your sample, the luminosity function is also really interesting for decoding galaxy formation through cosmic time. And so I like to think of this as this kind of very simple, not really even an equation, but really the luminosity function is the observed part of this equation. So we observe the galaxy luminosity function, but this is essentially has to be related to how the dark matter is distributed in the universe. So if we imagine we can see all the dark matter, and then we painted on top galaxies through astrophysics, which is obviously an enormous, complicated thing, then the result of that is what we observe as the galaxy luminosity function. So that means that we can tell something about both the astrophysics and the dark matter from what we observe in the luminosity or mass functions. So another way to kind of visualize this is shown in the left here, this nice cartoon from a review paper a few years ago here, which shows you how the galaxy luminosity function, the shape of it, can be thought of in relation to the dark matter distribution, which we know is kind of built upon. So if you take all of the dark matter halos at a given redshift, and you just took kind of simple estimates of how many baryons there were and how many stars you could form from those baryons, what you would predict for the luminosity function that we would observe is something like the red curve here. So this is something that's basically like the dark matter distribution, except that the mass has been converted into a luminosity using very simple assumptions, kind of the most optimistic assumptions, I guess you could say. But what we actually observe when we look at the shape of the luminosity function at many different redshifts, in fact, is something more like the blue curve here. So we see, in essence, fewer galaxies than we were expecting, both at the faint end and at the bright end. And it's not fully understood what's going on here. It's one of the big puzzles in galaxy evolution, but it's kind of hypothesized that this is due to feedback effects in these galaxies, which is stopping star formation from happening. So at the faint end, it's thought that in these very small dark matter halos, supernova explosions can actually expel gas from the galaxy outside of the potential well, and this then ceases or quenches star formation in these very low mass sources. And that's why we don't see as many as there are dark matter halos down here. For the most luminous galaxies, it's thought that potentially AGN feedback could be playing a part here. So in these high luminosity galaxies, the star formation rate has been again quenched or ceased due to the feedback from an accreting black hole in the center. So I'm really interested in this kind of hypothesis, particularly at high redshift, because at high redshift, do we really expect the same astrophysical processes to be working in exactly the same way as at low redshift? Because the chemical composition is very different, the stars are younger, the galaxies are not kind of dynamically relaxed. It's a very different situation at high redshift. And so I think by looking at the luminosity functions at high redshift, you can really start to see some interesting, possibly interesting effects due to different astrophysics. Another reason why the luminosity function is a really crucial measurement to make is that it's essentially measuring the luminosity is essentially measuring the star formation rate. And so if you integrate the luminosity functions to get a total, this gives you the star formation rate density in the universe. So yes, integrating the luminosity function gives you the star formation rate density. And this is a very famous plot, the Madaw-Lilly diagram, which shows you the star formation rate density on the y-axis with redshift. And there's this characteristic peak around redshifts 2 to 3, where this was maximal. The star formation rate in the whole universe was a maximum. I'm more interested in the right-hand side of this peak. And what you can see, interestingly, as derived from these evolving luminosity functions I showed you, is that the star formation rate density is rapidly increasing from redshifts 10 to redshifts 2. So it's kind of not surprising. As I said, we see it in the luminosity functions, but it's really nice to see on a plot like this how rapid this increase is, considering that this is a log axis. We have a factor of 100 in star formation rate density in the universe happening in the first billion years. I'm not going to go into this in too much detail, but this star formation rate density is also really important for the calculation of how reionization occurred. So reionization is the state change from neutral to neutral to ionized, and it's thought that this is due to ionizing photons from galaxies. And so to test this hypothesis, you need to calculate how many ionizing photons there are at a given redshift. And one of the key inputs to that equation, which is shown here, is this star formation rate density. So essentially, you need to know how many galaxies and how star forming are they to then work out how many ionizing photons there are in the universe. So moving beyond the luminosity function measurement then, what other properties do we know about these high redshift galaxies in the first billion years? Well, from the photometry, we have a few measurements we can make. So the first is a measurement of their color. And there, again, remember this is the rest frame ultraviolet color of the galaxy. And that's what's shown on the right here. So essentially, we just fit a power law to the rest frame ultraviolet. And the slope is parameterized by this parameter beta. It's not really important, but basically -2 is something that's very young and low metallicity. So we see that across a whole range of different luminosities, all of the galaxies at high redshift appear to be very young and low metallicity sources. We can also have a look at their sizes and morphologies in the Hubble data. And what we find is that these sources are very compact, typically irregular. Mostly they are just blobs. We can just about tell that they are resolved with Hubble. Sometimes they're a bit more interesting than that. But essentially they're very compact. So if you compare this half-light radius, 1 kiloparsec, to the Milky Way, for example, where it's 10 kiloparsecs or so, you can see how compact these early galaxies are. Okay, so I'm now going to change tack and talk a little bit more about work that I've done specifically on the most luminous galaxies we know in the epoch of reionization. But this is a good time if there are any questions so far. Sarah?
Yes, if anyone would like to ask a question, either raise your hand or put it into the chat window. A reminder that everyone joining this Zoom room joins muted. So if you do want to ask a question, please remember to unmute. So just wait a few extra seconds.
Yeah, no worries. Hopefully that means I explained everything perfectly. So
it's been very beautiful so far.
Thanks.
Okay, if there are no questions, then also remember you can put them into the chat window as we go along, and we'll have another call for questions at the end. Thank you.
Great. All right, yes, so this part of the talk is more focused on, as I said, work that I've done in the past few years, focusing not on the kind of typical galaxies that you find with Hubble, but on the most luminous sources. And I'll explain why they're particularly interesting in a second. So the first thing to realize is that the Hubble field of view, so the field of view that Hubble sees on the sky, is incredibly tiny. So compared to the moon here, if you just focus on this part of this slide, Hubble sees only a tiny patch of the sky. And what this means is that it can't find the rarest sources, basically. If the probability of a very bright, rare galaxy being in this tiny field of view is very small. So if we then look on the right here, the luminosity function at redshift 7, just as an example, what this means is that as we go brighter and brighter, the error bars firstly get larger because the samples are getting smaller and smaller, and eventually they just run out. There's no data points here. And the reason for that is to get a data point here requires a much larger volume of your survey than you can get from this tiny tiny little image from Hubble. So I hope that makes sense. So basically, we just need wider area surveys to find these more rare and bright galaxies and be able to pinpoint what's going on at this bright end of the luminosity function. So that's why I'm showing you this kind of brownish image here. This is what the VISTA telescope, which is shown on the top left here, can see in one shot. This is a VISTA telescope field of view compared to the Hubble field of view. So you can see that it's covering a much larger area on the sky, and this enables it to get a much larger volume to find these much rarer and brighter sources. So in the past few years, actually this is quite a while ago now, but I've been working on using data from ground-based telescopes in particular, which tend to have this much wider field of view, so they can look at several square degrees at once, to pinpoint what the number density is of the very brightest galaxies, and to get the first samples of the most luminous galaxies in the first billion years. And so you can see here results at Redshift 7 from VISTA data. We found a lot more galaxies than we were kind of expecting from this prediction, the gray curve here. And also we're able to make the first measurements extending the luminosity function to this very bright luminosity. So this was really intriguing, the results we found. So I should explain a little bit more about what this gray curve is. Let me just go back a second here. So the gray curve here is what we call a Shector function, and this is the kind of favorite function to fit luminosity functions at high redshift. And essentially it's a power law at the faint end, and then it becomes an exponential cutoff at the bright end. So that's why you see it kind of drops like a stone here. That's because it's got an exponential part. So this is what people were expecting to find in this regime. And what this would have meant is that I wrote these papers during my PhD, that I would have found maybe one galaxy or maybe no galaxies. That's what this prediction translates to in terms of what we would find in this data. But what we actually found was around 10, and that's why you see that it's in excess of what the prediction was. So this was really exciting at the time, these exciting new results that weren't what we were expecting. So the reason why this was particularly exciting goes back to this kind of cartoon image I showed earlier about how the luminosity function tells you a little bit about feedback in relation to the dark matter. So we hypothesized that the fact that we see a different shape at Redshift 7 could be due to a lack of quenching in these very bright sources. So potentially we could be seeing a reduced efficiency of AGN feedback, which causes the blue curve to go up towards the red curve, and we see a much shallower decline. This looks much more like the dark matter prediction without feedback. So we got very excited, but as with all science, there's a lot of things you need to check before you start making, before you start being very confident in your astrophysics. So there are a few things we checked to really work out if this was a true excess in luminous galaxies or not. So one thing to think about is, could this excess we see, sorry to keep switching, but this excess here, could it be due to gravitational lensing? So this question came about because what you find in the universe, if you look in regions where there is a high mass at low redshift, so for example, a cluster of galaxies at redshift 1 or so, that cluster gravitationally lenses all of the galaxies behind it, such that they are magnified. And what this can do is it can give you a distorted, magnified shape to your luminosity function. And an example of this is shown on the left here, where this is the data from a cluster field at Redshift 7. The underlying luminosity function is thought to be something more like this red line, but because of the lensing from the foreground cluster, you see this kick to the blue curve here. So we wanted to check if this was happening in our data. So I looked for clusters to see if there were very massive clusters in the fields I was looking at, and we didn't find any evidence for those. But the other thing we checked was what I'm calling here moderate gravitational lensing. I'm not sure that's the correct term, I should say that this is, so this is moderate gravitational lensing is not from a cluster, but from a single galaxy in the foreground. An example shown in this little image here, the high redshift galaxy is in the middle, but its flux is boosted by the fact that there's a redshift 1 or so galaxy very close to it along the line of sight. So we did a calculation of what this was doing to our measured luminosity functions, and we found that this moderate gravitational lensing is common, but it's only small, so it's only 0.1 magnitudes on average. So this is not enough to explain the excess that we find. The other thing we wanted to check was whether this excess in sources could be due to contamination. Now, I'm not talking about contamination from low redshift galaxies here, which would be a kind of incorrect redshift problem. I'm talking more about quasar contamination. So quasars at the same redshift in our sample. So the reason why this can be a problem is that if you look at the at lower redshift, the star-forming galaxy luminosity function looks something like this, as I've shown you several times before, in blue. But the quasar luminosity function, so these are galaxies, but where the light is dominated by the accreting black hole. These are very rare and very luminous, and so what you see is this orange luminosity function here. So you see it's the sort of the similar shape to the star-forming galaxies, but it's shifted down because they're very rare, and to the left because they're very luminous. So our selection can't tell the difference between a quasar and a galaxy at high redshift. And so we wanted to check, could our kind of excess that we see in the red points here be due to quasars? So essentially this orange part. Now, when we did this work, and even today, there are very few redshift 7 quasars known. They're very, very rare objects. Really just a handful of sources known. So to make a luminosity function is very challenging. And so what we did was extrapolate what was known at low redshift. And so if you just focus on this black curve here, this was what we predicted the redshift 7 quasar luminosity function to be. So the important thing is that this line is much lower than the points that we find. So we don't believe that this excess is due to quasars. So this means that we are confident that we're finding a different shape in the luminosity function at redshift 7, and we hypothesize this is due to different effects of feedback at high redshift, which is really exciting. So just to quickly highlight some work by my PhD student, Nathan Adams. He's been looking at the redshift 4 luminosity function, so a little bit lower redshift. And I just showed you that quasars can't explain our redshift 7 results, but this quasar contamination, in quotes, is an issue at redshift 4. I put contamination in quotes here because they are high redshift galaxies. It's just not quite what we're looking for. They're dominated by the black hole. So at redshift 4, this is what Nathan's work's been about in the last few years. There are many more quasars than at redshift 7, and there's a very rapid evolution in the quasars relative to the galaxies. And in fact, he finds that the quasars can make a big difference to the shape in the luminosity function. So these are really nice results I just wanted to share with you that show his points in red, where we have the galaxy luminosity function. It starts to drop off, but then we see this huge kick, and this is due to the quasars. Okay, so now I'm going to focus a little bit on some follow-up work we've done on these samples of very ultra-luminous galaxies at redshift 7. So this is the red points I showed you in the luminosity function. They're around, I said 10, but they're actually around 30 galaxies in those bins. And these are really luminous, and that means that we can follow them up and get very, very interesting results from other telescopes to understand their properties a bit more. So these sources were selected from ground-based data. So this VISTA data I showed you has this really great field of view. The problem with the ground-based data is that it is taken through the atmosphere, so the resolution is not as good as from Hubble. So a few years ago now, we asked for follow-up imaging with Hubble to try and get around this problem and to get the high resolution imaging we need to look at the galaxy sizes and morphologies. So this on the bottom left is just to show you again what a typical galaxy looks like. So a kind of fainter galaxy at Redshift 7 looks like in Hubble. It's just a blob usually, very slightly resolved, but basically not that interesting at all. And then to compare this with what we found for these very ultraluminous sources, again at Redshift 7. So this color scheme seemed like a good idea at the time, but basically it highlights that these objects are very, very clumpy and really, really extended, much more interesting than the typical source. And what we think is happening here is potentially these are mergers. So these are merging galaxies at Redshift 7, and it's the merging of these smaller, fainter galaxies that then gives a boost in the star formation that we observe. So really exciting. And these clumps themselves are separated by 5 kiloparsecs, which is really quite significant. I think I'm going to mainly skip this slide, but I just wanted to highlight that there are spectroscopy results. I've mainly based my talk on the photometry results because this is mostly what we have, but there are results from ground-based telescopes where they've looked at the spectra of high redshift sources. And in particular, what we're looking for here is emission lines, and the emission lines tell you a few interesting things. So the Lyman alpha emission line tells you if the source is in an ionized bubble or not. If the source is in an ionized bubble, you tend to see Lyman alpha. And there's been some evidence that these luminous sources are preferentially in ionized bubbles, which is kind of what you expect. Other detections of emission lines, so you can kind of see from this middle plot here how challenging this is. This is a very high redshift galaxy. It's very faint, and the emission lines are also very faint. So you can see it's really, really difficult to do this kind of work. But when we do find emission lines, this is really fascinating because it allows us to look at the ionization conditions of the gas that's producing these lines. So for example, the metallicity, also the hardness of the spectrum that's causing these lines to be produced. And what this has suggested is that these objects are low metallicity and they have a hard ionizing spectrum, which is again what you'd expect for kind of quite pristine stars at high redshift. So I'm just going to skip over that. So okay, another thing that you can look at is dust. So I really find dust fascinating, particularly when thinking about dust at high redshifts, because we don't know how it forms. So locally, we think dust takes quite a long time to form in the atmospheres of quite evolved stars, so maybe 1 billion years to form. But obviously, when we go back to the first 1 billion years, there's not enough time for dust to form in that particular pathway. So either there's a different pathway or there's no dust. And so over the last few years, there's been more and more detections of dust. This has been mainly due to this amazing telescope called ALMA here on the right, which is an array, sub-millimeter array, and this facility can detect the far infrared emission from high redshift galaxies. So in the first plots I showed, that dust bump, that's what it's detecting. And on the bottom right here shows you a Redshift 7 galaxy where we have detected dust. So again, putting limits on how this dust is produced in the first 1 billion years. And the background here is the Hubble image with the starlight shown as the kind of green. And then the ALMA data, which has quite a lot lower resolution, is shown as these contours. So you can see that there's a very significant dust detection there. And the really amazing thing about this is that we detected this dust in 10 minutes of telescope time, which is very, very short for a Redshift 7 galaxy. Sometimes people spend like 30 hours on other telescopes to get a detection. So these sources do have dust, and they are quite considerably dusty. Okay, so I think I have about 5 minutes left, so that's perfect. I'm gonna end my talk by looking to the future and how much better we can do in the next few years. And I'm going to illustrate this with this plot, which I actually dug out of my PhD thesis, which I quite like because it shows you kind of how much further we've got in how much further we will go in the next few years from that time. So this is a plot that just shows you, it's like a summary of all the current data and what we can do with that data. And on the y-axis is the survey area, which gives you the volume essentially. And on the x-axis is the magnitude limit of the survey. Comparing to other plots in this talk, because maybe the top axis is a bit more useful, which is the UV magnitude. And then the lines here are the kind of combination of area and depth that give you that number of galaxies. So just to clarify that a little bit here, this line here, the black line, n equals 1, this is the combination of depth and area you need to find one galaxy at redshift 7. So if you go deeper and have a larger area, or even just go deeper, then you can find more sources. So I hope that vaguely makes sense. But the dots here are the surveys we have so far. So basically, the better the survey, the more it is to the top right. Ideally, we'd want infinite depth over the whole sky, but that's never going to happen, unfortunately. So this is the compromise. Okay, so what can we do better now? So just to highlight the data I've been talking about to find these ultraluminous galaxies is this ultravista point here. So, well, sort of in between these points. So we found around 30 galaxies, which makes sense with my lines just about, and it's around 2 square degrees at 26th magnitude. So this is how much better we can do in the next few years. And the reason why we can start to push into this sort of top right-hand corner, which I said is much better, is because of 2 new telescopes. The first is Euclid, and Euclid is an ESA cosmology mission. In fact, its primary goal is cosmology, but it also has optical and near-infrared filters on it. They extend to around 2 microns. And when it's launched in 2022, 2023, it's going to do a very deep survey here, which is around 40 square degrees. 2 similar depths that we have currently. So this is going to increase, if you can read these lines, the samples by factors of 10 to 100 of these luminous galaxies. The other telescope that I'm really excited about is the Nancy Grace Roman telescope. This is a NASA telescope, which is essentially a Hubble. It's a Hubble, but it does wide areas. So whereas Euclid is actually a cosmology mission that we're kind of hijacking for high redshift studies, the Nancy Grace Roman telescope is more specifically for galaxy work. It has more bands, it has 7 bands, and it will be launched a little bit later. But you can see that the Roman surveys are going to be even more powerful than Euclid at finding large samples of these distant galaxies. So this is kind of hard to visualize. So what I did was I made simulated luminosity functions that we can expect to get from these data, from these new telescopes. So this is the Redshift 8 luminosity function, just to pick one. So this is 613 million years after the Big Bang. The grey points are mainly from Hubble surveys. Well, okay, so leftwards of this point, they're mainly Hubble surveys. And then the red points are the best that we've done so far with ground-based telescopes. So you can see we push out to brighter magnitudes with these ground-based telescopes. So what do we get if we use these new surveys in the next few years? Well, unsurprisingly, it depends on what happens to the luminosity function. You know, does it continue like I've hypothesized as a very power law type thing that's a bit more like the dark matter, or is there this sharp cutoff that we see at low redshift? So in the optimistic case, this is the predictions I made for the Euclid survey, if there is this kind of more power law type decline. So you can see we're going to get amazing constraints on this slope, and along with that, samples of thousands of galaxies, which we can then look at the sizes, the morphologies, their colors, this sort of thing. So it's going to revolutionize the field. In a slightly more pessimistic scenario, where we have this exponential cutoff here, we will find fewer galaxies, but fundamentally, I don't really mind which one it is, so long as we then work out what's happening with the astrophysics. So if this is the case, then that is also really interesting. It's telling us that these feedback effects do switch on. much earlier than we might expect. And this is just a little table. I'm not going to go into it in too much detail, but that shows the numbers we predict depending on the functional form. So the Shector is the steeper one here. But even in the worst case scenario, we expect to find 30 Redshift 10 galaxies, of which there are only a few known today, and maybe even a few Redshift 11 and 12. And again, remember, these are very luminous sources, so we can then follow them up with other telescopes. And in fact, I think that's my last slide here, which is a very brief mention of the James Webb Space Telescope and how amazing that's going to be as well in combination with these other surveys. So James Webb is primarily going to do spectroscopic follow-up of these very luminous galaxies that we will find with Euclid and Roman. And one of the most exciting things I'm looking forward to with James Webb is that it can do integral field spectroscopy. And all that means is that for every pixel in this Redshift 7 galaxy, we will get a spectrum. So that means if there's a black hole, active black hole hiding here, we'll be able to see that in the spectrum. And if there are metallicity gradients, for example, in the galaxy, which tells us about how the gas is accreting, we'll be able to see that as well. Yes, just an incredible amount of information that we're going to get for these galaxies in the next few years. So with that, I will end, just summarize with a few take-home messages then. Observations of galaxies at high redshifts, which I'm defining as redshift greater than 5, reveal the earliest stages of galaxy formation and evolution. We are now very successful at selecting samples using this Lyman-break technique, which we use on the rest frame ultraviolet, and we can see the evolving number density with the UV luminosity function. My own work has shown that some of the most luminous sources seem to be more numerous than expected, and this is possibly due to reduced AGN feedback at early times. But this will really be revolutionized and sort of made much more robust with new telescopes such as Euclid and Roman, which will produce many, many larger samples that can then be followed up in exquisite detail with James Webb. And with that, I'll end. Thank you for your attention.
Please unmute if you'd like to join in the applause.
Should I stop sharing or should I?
Yes, if you'd like to, or if you want to leave them up, that's also
I'll just
fine.
leave it up, yeah, just in case people have questions though.
Okay, no worries. So yes, do we have any questions from the floor to start with? Yes, from Clinton Stevens, they've asked, could you comment on the distribution of AGN at high redshift before and during the epoch of reionization, i.e. what is the ratio between AGN and star-forming galaxies at this redshift? I'd like to know how much AGN could have contributed to reionization. Great talk, by the way, thank you.
Thanks, that's great. Yes, a brilliant question. Yeah, so this is a current hot topic in the field, is how many quasars there are or AGN there are, and how this could change their contribution to reionization. So I'm not sure if I can find a slide that's actually helpful. Right, here we go. Right, so I'll show Nathan's work. So what this comes down to is there are not many bright quasars. So we know quite well that there are a lot more galaxies than there are quasars. But what we don't know is how many faint quasars there are. And it's the faint objects, the faint accreting black holes, that are the ones that would contribute to reionization, because there's just not enough of these ones up here that we know about. So to know this and to know their contribution, you have to extrapolate considerably beyond what is known, kind of demonstrated by this dotted line here. And the predictions, I can't think of the word, but they're very different between different studies. So some people have a very flat slope, which means there's very few faint quasars, and other people have a very steep slope, which is completely different. And the current controversy is whether, if there is this very steep slope, maybe we don't need galaxies for reionization, and maybe we only need quasars. And so I can't give you a definite answer because nobody knows, but you've hit upon a very important point, and it's something that I'm very excited to see what happens. You know, are there many black holes accreting down here and we just don't know about them yet?
Very cool. And before I miss it, there was also a comment from Benjamin Hugo, who said, "Thank you for the great talk, Rebecca."
Oh, thanks very much.
Another question, and then I'll go to Josh, who raised his hand. Stabile has written, "This has been a very interesting talk. Thank you. I missed some of the talk. Forgive me if this is a redundant question. Do Lyman-break galaxies at redshift 6 to 7 tend to reside in high density groups and clusters?"
Mm-hmm. Yeah, another great question. It depends, I guess, is the answer. It depends what sort of galaxy that you're talking about, because there's a distribution of galaxies, and the most, I can't think of if I have a plot to show this. Wait a second. How do I escape? There we go. So let's go to my realization picture. There we go. So galaxies cluster together, but there are also field galaxies, right? So it depends really on how they're forming within the cosmic web. But it's thought that the very high redshift sources are strongly clustered, so they do reside in these high density regions. And that's purely because this is where the different filaments in the cosmic web are sorry, my words have just gone today, coming together. And so these are the high density regions. So it's thought that the first galaxies were very strongly clustered together. But over time, we do start to get a more distributed view, and more galaxies kind of filling out the distribution. Hopefully that vaguely answers your question. I'm not sure.
Awesome. Yes, it does. Thanks.
Great, thank you.
And Josh, would you like to ask your question now?
Yeah, first of all, thanks a lot for this great talk. So you showed this velocity field of a very distant galaxy, which looked like, I mean, that was ALMA, I think.
Yeah.
So how many of those either, are those also to be expected to come from the stars? Or, and how many of those do we expect in the next few years to get?
Mm-hmm. Yes,
so,
great. Sorry, yeah. So yeah, sorry, I didn't mention this. I was just kind of running out of time, so I skipped it. But yes, as you rightly say, this is a velocity map, and it's determined from ALMA. So it's from the C2 emission line. So that's coming from the kind of neutral ionized gas, like the photodissociation region around these stars. And so it typically tells you the velocity field of the stars as well. I think that's what you asked, right? So it's telling you. I'm not saying this very clearly. It's from the gas, but the gas is ionized by the stars. So it gives you an idea of what the velocity field of the stars is. And this particular paper was actually of the same galaxy on the right here. So the two clumps there correspond to these two clumps here in the C2. And they use this for evidence that this is actually a merger, because you see kind of two different velocity clumps there, rather than a disk. And so to answer the question about, how many more of this kind of data will we get in the next few years, I'm part of a ALMA large program, which is called Rebels, and they targeted 38 galaxies very similar to this at redshift 7. And that's the highest redshift large program that I know about. And that should give similar quality data to this for around 38 objects.
This will all use ALMA and no other frequencies tracers.
So we can't do this with optical near-infrared spectra at the moment, because they're so faint. This C2 line is very bright. I showed you some of this. We might get other ionizing lines, but they are very faint. What we hopefully can do is this with James Webb, though, because James Webb will give us the rest frame optical lines, so the H alpha, O3, that sort of thing. So that will give us a different tracer of the same thing.
And that's not rotating disk? It looks like it.
I'm not part of this paper. They claimed it was a merger. So okay. Yeah, it's hard to say. Thanks.
Very cool. Are there any more questions from the floor? if I may ask a question then. So you mentioned James Webb being used to follow up sources.
Yeah.
Are there any plans for it to observe like a patch of sky, following on from your idea of wide area giving you the volume for rare objects?
Yeah. So I didn't mention that, but yes, but James Webb has an even smaller field of view than Hubble.
Mm-hmm.
So James Webb will be really cool because it goes redder than Hubble can. Like on that video I showed, whether it becomes invisible in the Hubble bands, James Webb will be much redder, so it can find higher redshift sources. But in terms of its survey areas, they're like 100 square arc minutes, so really, really tiny survey limits. And it's just so difficult with a small field of view to get the area you need. So that's why I focused here on the follow-up. Right. We find the sources with the wide area and then follow them up with James Webb. I think that's the best we can do.
Awesome. Very, very cool. Thank you again for an excellent review, Rebecca.
You're welcome. Yeah, it's so nice to be here and to talk to you all today.
Thank you. I'll just stop recording now.